and gentlemen. A warm welcome to each one of you who are present here today for the inauguration ceremony of the 10th Ruhuna International Science and Technology Conference 2023, organized by the Faculty of Science, University of Ruhuna. We are very excited to note that this year's conference will be conducted under the theme of Advancements in Multidisciplinary Scientific Research towards Environment Sustainability. So, ladies and gentlemen, once again for giving us the gift of your presence here in this morning, and also I warmly welcome you all, our chief guest and our other dignitaries, to join us with the lighting of the traditional oil lamp. First and foremost, I would like to invite our chief guest, Senior Professor Sujeeva Amarasena, the Vice Chancellor, University of Ruhuna. Our keynote speaker, Professor Gomika Udugama Surya, Associate Professor, University of Houston, USA. Professor Mrs. D.H.N. Monasinghe, the Dean, Faculty of Science. Mrs. C. Senaviratna, Acting Registrar, University of Ruhuna. Mr. Gimal Hettiarachchi, the Librarian, University of Ruhuna. Mr. S. Dilnage, Works Engineer, University of Ruhuna. Mr. D. L. Eratna, Deputy Registrar, Legal, University of Ruhuna. Senior Professor, Thank you, ladies and gentlemen. May our lives be enlightened with the light of this lamp. Now it's time for us to formally commence the event. So I humbly request the entire gathering to rise for the university anthem. Thank you, everyone. Ladies and gentlemen, without much ado, I respectfully invite Dr. T.G. Dayananda, the chairperson of the 10th Ruhuna International Science and Technology Conference 2023, to welcome all of you with the official welcome address. Over to you, sir.
Good morning. Senior Professor Sujiva Malasena, Vice Chancellor of the University of Ruhuna, Professor EPS Chandana, Deputy Vice Chancellor, the keynote speaker, Professor Gomika Udukamasuriya, Professor D.H.N. Gunasinghe, Dean, Faculty of Science, Deans of other faculties, heads, senior professors, and all academic staff, acting registrar, deputy registrar, librarian, distinguished guests, sponsors, non-academic staff members, ladies and gentlemen. A very good morning and productive day to all of you. It gives me an immense pleasure indeed to welcome you, your esteemed presence at the 10th Ruhuna International Science and Technology Conference, which is one of the most eminent, scholarly and prestigious event organized by the Faculty of Science, University of Ruhuna. Today, 2023, 18th January. I am very much delighted to announce that Faculty of Science is celebrating the 10th anniversary of Ristcon. As you all can perceive, it has not been a smooth sailing. We had to encounter many twists and turns, but today, as a faculty, we all could be delighted looking at where it stands. When we look back at the past 10 years, it is evident that Ristcon, which has gained tremendous recognition among Sri Lankan leading scientists and researchers, has made a remarkable progress over the course of time. Thus, I believe that it is my responsibility to work you through the background of Ristcon organized by the Faculty of Science. This was initiated in 2002 as Science Symposium, and owing to the prompt dedication of academics of Faculty of Science, University of Ruhuna, it was upgraded to be on par with the international level in 2014. Giving birth to Ristcon, Ruhuna International Science and Technology Conference. Today, it stands out as the most prestigious scholarly event conducted by the Faculty of Science. For Ristcon 2023, more than 170 abstracts were received. Only about 125 abstracts were accepted after a stringent reviewing process. So as the chairperson of the organizing committee, it brings me a great sense of pleasure and an honor in welcoming you all to this historical event, which marks a landmark in the history of Ristcon. First and foremost, I would like to welcome the chief guest of the event, Senior Professor Suji Vamarasena, whose distinctive guidance and decision steered this prestigious event to be materialized. I am privileged to welcome Deputy Vice Chancellor Professor Saman Chandra, although he is absent because of he has some other commitment, other appointment. Anyway, I welcome him also. It is much respect and honor. I welcome Professor D.H.N. Munasinghe, Dean of the Faculty of Science, whose zealous commitment and vision committed to make this venture a success. Presence of deans from other faculties of the University of Ruhuna is highly appreciated, and I cordially welcome you all too. Very honestly, I would like to immensely acknowledge the keynote speaker, Professor Govika Ududawasuri, who has made a great landmark in the field of research with his sincere dedication, commitment, and devotion to duty. Sir, your presence here to grace this occasion is indubitably an honor for us. So I am very proud to welcome you warmly to the 10th Ristcon University of Ruhuna Faculty of Science. Your presence today with us here indeed adds glamour to the event. Further, I would like to extend my warm welcome to all the senior professors, head of departments, and all academic staff, especially members of the 10th Ristcon Advisory and Editorial Board, members of organizing committee, and the academic supporting staff. My loving welcome goes to Professor Mahinda Pantu, Director Quality Assurances. Also, I welcome you too. Then I would like to welcome Acting Registrar, Mrs. C.N. Chandrika, the librarian, Mr. Nimal Hekyaranchi, Mrs. Chandima, Acting Assistant Registrar, Faculty of Science. Let me welcome our sponsor, representative, and I warmly welcome them too. Your contribution at this crucial time was paramount important to this event. Finally, I welcome all scholars, authors, non-academic staff members of the media unit, then members of the media unit, members from Ink of Photography Club, all non-academic and all the other participants who have gathered here and also who have joined through the cyberspace to be a part of this remarkable event. All of your participation is indeed a strength for us. Finally, I would like to say that if not for the hard and painstaking duty and the dedication rendered by the organizing committee of Ristcon 2023, this event would have been just a dream. Highly appreciating their contribution, I finally wish that this event would be a great platform for all of us to share and further our horizons. Wish you a very good and productive day. Thank you.
Thank you very much, sir, for that warm welcome. The annual research conference of Faculty of Science aims to provide the premier multidisciplinary forum for leading academics, researchers, research students to present and discuss their innovations, concerns, practical challenges encountered in a variety of disciplines such as science, engineering, and so on. So the success of this event is a support and commitment of a large number of academics and the staff in the Faculty of Science. She is a driving force behind this event who gave us the right guidance, assistance, and countless support to make this massive event a success. Hence, I respectfully invite Professor D.H.N. Monasinghe, the Dean, Faculty of Science, to address the gathering.
Good morning to you all. The chief guest of the event, the Vice Chancellor of the University of Ruhuna, Senior Professor Suchiva Amarasena, the Chairperson of the Ristcon 2023, Dr. C.G. Dayananda, and especially the keynote speaker, Professor Govika Udukamasuriya, plenary speakers, Professor Tutika Marbe and Professor Chandima Gomes, and all invited guests and participants. So it is indeed a great pleasure to address this inaugural session of the 10th Ruhuna International Science and Technology Conference, giving you several words in this morning. Ristcon was started, as Chairperson mentioned, in 2014 as a continuation of the symposium of the Faculty of Science. And I want to mention here that I was privileged to be the first secretary for the Ristcon 2014. So that time it was a 2-day event. I can remember we organized 2 days, but with the constraints now we had during past few years we have to limit it to a 1-day event. And this time it is 1-day event with 2 modes, physical and online mode we conducted. The theme of the Ristcon 2023 is Advancement in Multidisciplinary Scientific Research towards Environmental Sustainability, which is a timely, important topic they have selected for this event. The environmental problems are one of the biggest challenges in this century. The world today confronts a multitude of environmental problems, more than even before, over a wide range of spatial and temporal scale, and it is impacted by various interconnected factors from different disciplines such as physical, biological, social, legal, political, cultural, etc. So today it is a challenge to recognize the ramifications of interdependence of such factors, because these environmental problems cut across various disciplines and their boundaries, and therefore cannot be resolved from a single perspective. Therefore, it is well recognized that protecting and preserving environmental qualities require input from multidisciplinary approach. So at this point, we cannot forget the traditional knowledge that we had previously and practically used it in the past with utmost success. And that has not been well understood in the context of the modern science. Exploration of this knowledge using multidisciplinary approach would be an opportunity for scientists to enhance their understanding and to create new avenues to find solutions for these environmental problems. So in that sense, this year, Ristcon has selected 125 abstracts, as I heard, from 179 they received, to present at the conference under different categories. So I actually thank those researchers, even though with hard time, with the crisis in the country, they still conduct their research in a successful manner. Then they were able to present their findings at this conference. So I believe that it will be a forum to disseminate knowledge, what they gather from their research among the scientists from different disciplines, and it will be an interesting and fruitful day for you all with many kind of information that you can gather from their with the technical sessions they're going to conduct in this afternoon. Finally, from behalf of the Faculty of Science, I would like to thank all who contributed in this forum or Ristcon 2023 in different ways, such as invited guests, speakers, and reviewers, presenters, and evaluators, as well as all the staff who were behind the screen to make this event a success. I congratulate the team, organizing team, with the chairperson and all the members of the team, and for their commitment and tremendous effort they took into this event make a success. Over the past year, we know we had many discussions, they had different problems in the different ways. So they overcome all these problems and now it became a reality today. So I congratulate them all and I wish you all the best and a fruitful day ahead. Thank you very much.
Thank you very much, Madam. We are at the much awaited item on the agenda. Ladies and gentlemen, now it's time for us to listen to our keynote speech, and it is indeed an honor to introduce our keynote speaker today, Professor Gomika Udugam Surya, Associate Professor, University of Houston, USA. To introduce our keynote speaker to the audience, now I call upon Dr. M.S. Kodikara, the Joint Secretary of the Ristcon 2023. Over to you, sir.
Thank you. Good morning, everyone. The Vice Chancellor, Dean, Faculty of Science, Deans of the other faculties, academic staff members, distinguished guests, ladies and gentlemen. Today I have the honor to introduce the keynote speaker of the 10th Ruhuna International Science and Technology Conference 2023, Professor Gomika Udugam Surya. Professor Udugam Surya obtained his BSc Chemistry Special in 1999 from University of Colombo and PhD in 2006 from Wayne State University, USA. Then he completed a postdoctoral fellowship at University of Texas Southwestern Medical Center and joined the faculty at the same university in 2009. He moved to University of Houston and MD Anderson Cancer Center in 2014 and currently serving as Associate Professor of Medicinal Chemistry. Professor Udugam Surya is directing a multi-million cancer research program mainly focused on cancer drug-led discovery and diagnostic tool developments funded by various sources such as NIH and Department of Defense. Regarding his publications, he has published more than 40 research articles in world's topmost journals, including Nature Chemical Biology, Journal of American Chemical Society, and European Journal of Medicinal Chemistry. He also presented over 75 conference papers and delivered speeches at about 50 invited seminars in US and worldwide. Furthermore, he introduced a novel two-color high-throughput drug discovery technology and has 8 patents so far. He is an editorial board member and a reviewer of many international scientific journals. Also, he is a member of grant review panel in the US government National Institute of Health, private foundations such as Keck Foundation and multiple international institutes. To appreciate the contribution made by him, he received numerous awards, including University of Texas, 50 in 5 Scholar and Faculty Excellent Research, and NIH Career Development Award, and University of Texas Metroplex Science Award. Professor Ruhuna Surya is the chair of the Graduate Education Committee at University of Houston, and he has been advocate for many young scientists and engaged in numerous career building seminars and workshops, both in US and Sri Lanka. Therefore, I certainly believe that the conference will expose fruitful results from the keynote speech, which will focus on the wisdom beyond chemistry, novel technologies to expedite the modern drug-led discovery process. Ladies and gentlemen, with great pleasure, I would like to invite Professor Bhumika Udugamasuriya to deliver the keynote speech of 10th Ruhuna International Science and Technology Conference 2023. Thank you.
Good morning to you all. Thank you very much for that kind introduction. And I want to greet the Vice Chancellor, Professor Amarasena, and the Dean of Science Faculty, Science, Professor Singha, and all the distinguished invitees and the participants. So it's a great pleasure for me to give this keynote speech, especially in Sri Lanka, and I have delivered multiple of those, so I'm very glad to be in Ruhuna University as well. So today, and also I want to thank Dr. Dayananda and the organizing committee for me to give this opportunity to talk to you about the wisdom of chemistry beyond the chemistry. And I have been envisioned for a long time, and I know this is a very diverse audience, so I'm not going to talk about chemistry. I'll go beyond that, and I'm definitely I'll be in the biology, biomedical sciences. So, and I want to tell you, like, I have a lot of data slides latter part of my talk, but I will go very rapidly on those just to show those slides are there. But I'll try to give you an overall view of what I have been doing for like past 15 years of my independent career, and I hope this works. Is this working? Okay. So actually my title was Wisdom Beyond Chemistry and Modern Novel Technologies to Expedite the Drug Discovery Process. So this is the scary drug discovery process we have in the Western research process. So if you enter like 10,000 compounds at the beginning, only one become a drug. It has to go through the initial laboratory testing and then the preclinical animal testing, and there are 3 phases of human trials, and then only one become a drug. And the statistics even really scary. You need to spend like $1 to $2 billion, and it takes about 10 to 15 years for one drug to come after we input 10,000 active compounds at the beginning. So you all also see, and I have a big problem with this process. It looks very wasteful process, but this is how it happens. So this is another slide I'm showing, the drug output compared to the research and development funds we input. So in the blue, you see the research and development funds are really increasing, but the drug output is steady, it's not increased compared to the investments we, the expenditures we use for the drug discovery. And this is a problem. And then this slide shows how many drugs come out per $1 billion. And over the time, it's been decreasing, and now it's about only one drug comes out of about $1 billion. this is a problem. So I was actually thinking about what we can do to expedite this process. Now, in general, what happens is biologists find the targets that are important for various diseases, and then the chemists come forward and develop drugs to target those biomarkers to address the disease condition. And then only we look whether that molecule has off-target effects, side effects, whether it affects the normal cells. For example, if you take a cancer cell, we target various biomarkers to control the disease, but later we find most of them have a lot of side effects, off-target effects. So in my approach, when I was thinking about that, I was thinking can we bring this normal cell effect, off-target effects in the very first day of the drug discovery. If we can do that, we can at least save some time. So how can we do that? So in my approach, my lab actually working on targeting cell surface biomarkers for various diseases, mainly for cancer. So there are two major biochemical tools I want to introduce: the molecular class we are working on, and then the unique technology that I developed about 10 years back. So in drug discovery, there are two major ways of doing this drug discovery. One is structure-based drug discovery, which is like we take the keyhole and work on cutting the key to that keyhole, working one molecule at a time. The second approach, which is currently used hugely, is the high throughput screening. So that means we bring all the keys and then allow the keyhole to pick the best one. So, and then we can utilize them for diagnosis as well. So in my approach, we are working on the high throughput screening. These are the three major clinically approved drug classes: small organic molecules, peptide drugs, and then the antibodies. I think we're all familiar with those different molecular classes. And the molecular class that I work on is a new molecular class called peptides, which is derived from peptides to overcome various problems. So this is the difference between a peptide and a peptoid. So in a peptide, it's built with the amino acid sequence. In peptoids, this side chain, which is on the alpha carbon, is moved to the amine nitrogen. With that, these peptoids are highly serum stable, non-immunogenic, small cell permeable, highly diverse. There are a lot of great characteristics as drugs. And I'm very fortunate to interact with the father of this molecular class, Professor Ron Zuckerman, who introduced this in the 1990s. And then also the second father of this molecular class, Professor Thomas Kodelek. He was my advisor for my postdoctoral fellowship at the UT Southwestern Medical Center. So I have two chemistry slides, please bear with me. And I will stay away from that after that. So the peptide synthesis is very straightforward. We build those on a solid beads, and it's just like the amino acids addition. Peptide also built with two chemical reactions, mainly coupled with amines, and I'm not going to go into the details, but I mentioned we are doing high throughput screen. That means we develop large number of compounds, libraries for the screening. So how do we develop these libraries? Let's say there are three building blocks called ABC. And then we take three reaction vessels and couple A here, B here, and C here as those three places as the first residue. And then we mix them and then randomly separate them back to those three vessels. Now each vessel has all three now. And then again, as the second residue, we couple A, B, C in the same place, same reaction vessels. Now, you see there are 9 combinations, 9 different compounds on those B's, right? So if you have more amines, more steps, you can go to very high numbers. And this is, I'm showing an example of like quarter millions of compounds we develop in our labs. And The reactions are done under microwave conditions within less than a minute. So it's within few days we develop this very large number of compounds. Quarter millions here, this is another library for 400,000 compounds. Okay, so what will happen after develop these libraries? Each bead has a unique sequence and there are a lot of copies on that. And different beads have different compounds. So how do we find the drug lead or the best compound for our target? So the method that was existing by the time I developed my technology was we overexpress, engineer the target we want to develop a drug, which is like for an hormone, enzyme or signaling molecule important for a disease, and then with a tag we expose it to the beads, and if it binds to a molecule on a bead, that bead get light up, so we pick it up and identify the sequence. That means we have a drug lead for that protein, right? So that's the conventional way of doing that. But again, we don't know that compound affect normal cells or it has off-target effects. That's still the conventional drug discovery process. So this has been there for about 2 decades, and then I thought about how to address this off-target effect, at least on a certain level. So what I did was, I took whatever the receptor we want to target and express that on the cell surface and leave it in the natural condition and expose to the library, but with a very important control. So in this case we use this vascular endothelial growth factor receptor, which is we call VEGF receptor 2, which is very important in cancer growth. So the tumors cannot grow beyond a few millimeters without the blood supply. So what happens is this VEGF hormone is secreted by the tumor cells and they go to the nearby blood vessels, which has these VEGF receptors, and bind to that and tell those blood vessels to form new blood vessels towards the tumor, bringing the nourishment. So if we can block this receptor, we can starve it, and it's been well validated. There are drugs available. So to develop this technology, I use this receptor system. So the idea is, took a cell line, divided into 2 groups. In one group, we overexpress this VEGF receptor. So ideally, these 2 cell groups are equal. The only difference is if there are 1,000 molecules, the cell line shown here in the left has 1 receptor excess, which is the VEGF receptor. And then I did a very kindergarten thing, very simple thing. So what I did was I stained these receptor positive cells in red and the parent cells in green, mix 1-to-1 and expose to these library beads that has those compounds. And then, I don't think I can point easily, so if you see on the right bottom, the middle area, there is only a bead that has only red cells bound. And if we find that type of a bead, what it indicates is, if you look above, the compound on that bead binds to the receptor we want to target, in this case VEGF receptor, and it doesn't bind to any other cell surface molecule. If it binds to any other cell surface molecule, those are present in the green cells, and you will find both red and green cells bound, the very right bottom type of bead. That means we can eliminate all these off-target, the compounds that has off-target effects at the very first day of this discovery. I hope you followed that. This is the principle. So it's very sensitively detect the difference between 2 cells surfaces and only find compounds that are very specific for our target. Okay. So these are actual fluorescence microscope images. I don't know whether you can see on the left side, you see the real full red cell bound bead, which has a compound very specific for this VEGF receptor. On the right side, I'm showing those beads that has both red and green bound. That means they are the compounds may bind to the VEGF receptor, but they are having off-target effects. So we eliminate them at the very first day of the drug discovery. Otherwise, we would have gone like years of time spending and money and resources, and then at the end we find they are non-specific. Okay, that's the principle, and this is one of the summary of one of those compounds we found. We've published a lot of papers on the anti-cancer activity up to preclinical levels. It's been discussed to take it forward as well, and then we use it to deliver imaging agents also for the diagnosis of the cancer. Okay, so this kind of give a overview of what we are doing. So this is only one project, and this is where I started my independent career, University of Texas Southwestern Medical Center, and then I moved to the MD Anderson Cancer Center and the University of Houston, and combining with these institutes and few other institutes, the Texas Medical Center is formed, which is the largest medical center in the world. These are a few pictures of my lab. Anyway, so I'm going to show a few projects that we have spearheaded using this novel technology. So the first one I'm going to talk something very commonly known, which is the targeting COVID-19. This was one of the very latest projects that we started. So I think you all know how COVID get infected through the nose. So what happened is this virus has this S protein on its surface, and it binds to this human ACE2 receptor, which is the angiotensin conversion receptor. So when this S protein interacts with the ACE2 receptor, it's like it grabs the doorknob and get into the cells. That's the primary mechanism for these viruses all the SARS viruses to enter the human body. Now, if you think the simplest way to block this infection is to put a roadblock there, right? So if you try to target the S protein, it gets mutated, it's not going to work. If you target the ACE2, that will be the best way. Now, for the SARS viruses, the COVID is the third one. So the SARS viruses, this mechanism has been known for 2 decades. So I was really wondering why no one has tried this, because this is the simplest way. Actually, people have tried, but there is a problem. The biggest problem, actually the idea for doing this is to develop nasal spray like drug, so you can spray and go to work. It's actually basically the molecular version of the face mask. So basically trying to put a face mask between this human ACE2 and the virus S protein. But the area that I just highlighted is the critical thing. So what is this ACE2 receptor? It is very important for our blood pressure regulation. So if we develop anything that hits that receptor, it can be immediately toxic for us. So that's the biggest problem. No one was able to develop a compound that can block the virus entry without become toxic to us. But actually there are molecules reported, but none has become a drug. So, but when I thought about this, I didn't give up, because virus does that, right? Virus touch the receptor and get it. So then, when I look at the structures, so what happened is, so that if you have the receptor like this, and you have this active site here, and then the virus touches different place, and very cunningly get into the body without affecting this. So it doesn't cause toxicity to us immediately. So for the general conventional drug discovery cannot target easily for this type of situation, because the tools are there to target this active site, the keyhole, right? Like I mentioned. So my hypothesis was, if we mimic exactly when the virus came in the evolution, we may find the place. So that was my hypothesis. And then actually I have the tool to do that. So the idea is to mimic this exact process where the virus comes in and binds to that receptor. And if you can remember, we have compounds on beads the peptoids display on beads, and that kind of mimicking the virus. So that's what I did, and we did this 2-color assay, and to cut a long story short, we found 2 compounds from 50,000 compounds screen. And I forgot to mention, this is actually my lab now, about few hours work, so we do 100,000 compounds per day. We showed that it binds to the receptor, and we showed it, we did the quantifications, and then also we showed that our compound can block the ACE2 virus S protein interaction, and also very importantly we showed in the cellular level virus entry has been blocked. So this is all cool, but the biggest question again and again is it toxic? So we checked our compound on various cell lines, and the compound is not toxic to any of those cell lines on the concentrations we use. And also we showed that the compound is not affecting the receptor protein structure. And also, very importantly, we showed that this compound has no effect on the enzymatic function. So, both in the biochemical and cellular level. So this is really cool. And we did the molecular docking, and then we found that our compound almost exactly binding to the place where the virus binds. So it looks, my hypothesis worked there. So we were very excited, and now actually it's been moving to the preclinical levels. These are work now. We are doing a lot of studies on the mice and the hamsters, and I'm not allowed to talk about those data because it's been done through the company. And I want to share this slide. When we published this paper, I got an email from a very unique person in US. If you see the rightmost person, gentleman with the hat, I don't know whether you can remember, he's Mr. Aloe Black. He's a Grammy Award nominee singer in US, and his songs were become #1 in 22 countries or so. Anyway, so I got an email from him. What happened was he had the COVID, and he was looking for different solutions. And our solution is very different than vaccines and other things, so he got very attracted. And again, to cut a long story short, we had discussions, and now he has been funding our project with several $100,000 has been pumped into the project. And this was a news release came just a week before, so I just wanted to share that story as well. So the idea is to develop, block this interaction and develop a molecular version of the face mask. Okay, now that's actually a recent project. I mentioned my work is mainly on the cancer research. So this is a very complex area, and we don't have a real drug that we can say, okay, there's a drug for cure cancer, right? Why is that? So it's mainly because of the real huge heterogeneity present in these biomarkers. So the first problem is these biomarkers are very different from cell to cell, person to person, and even cell to cell. So it's like if a village is a cancer, if we can open one house from a single key, but that cannot open the other house. So it's such a complex situation. Now I showed you the targeted drug discovery. Now when this was initiated like about several decades back, everybody thought we can solve the cancer problem, but it is not, we all know. The reason is the biomarkers, the targets are very heterogeneous. They are different from person to person and also from cell to cell. And also the signaling cascades are very different, and they are very complex. Like, for example, if you take Sri Lanka as a cancer cell, and if you want to block an outside growth signal comes from, let's say, through the airport, and the message goes to the candy, like the nucleus. So we want to block the airport, but the same message comes through the harbor and go to the same center, right? So the targeted drug discovery is in a real challenging situation when it comes to the cancer. So that's another problem. And then there are very strong cell types in tumors, they are called cancer stem cells. So normal cells, usually the cells can just divide. A skin cell can form only a skin cell. But these stem cells can be not only divide, they can differentiate into different types of cells. So when these stem cells become cancerous, they form these highly heterogeneous tumors. So conventional drugs can destroy most of the tumor cells, but not the cancer stem cells. So they bring back the tumor. So that's another huge problem. So these are most of the problems that we try to address in my lab. And so I'm going to show you a few more examples based on this technology. So once again, I showed you typically in drug discovery, biologists find the targets for diseases, and then chemists come and develop drugs, and then only look for the normal cell whether it has soft target defects, right? In my approach, I'm trying to bring those two together. So what I basically do is compare the disease cell and the normal cell and identify these drug leads that only bind into the disease cell, in this case cancer cells. When we do that, this is go one step back from the molecular level and go to the cellular level. So this is actually reversing the conventional drug discovery process, because we don't know the target first, but we know the target is only on the disease cell, and it can be a protein, lipid, carbohydrate, or whatever the molecules that only found in the disease cell, in this case cancer cells. Okay, so let me give you one other example of how we do this unbiased selection. Now in this red and green screening, we use it to target a known target, right? I explained that is using VEGF receptor targeting. Now this is complete unbiased selection. So the idea here is target cancer stem cells. Actually there are no proper way to target these cancer stem cells. And also there's no drug available directly targeting cancer stem cells. There are drugs that can target the stem cell signaling, but not the exact path for the cancer. So, like I said, the conventional drugs can get rid of most of the cancer cells, but these cancer stem cells remain and bring back the tumor. So, if we can target the cancer stem cells, we can destroy the complete tumor, because we are removing the governor of the tumor. So, like I said, there are not much biomarkers known for targeting cancer stem cells, because the biology is very complex. There are some, but they are also very heterogeneous. So this is where my technology was applied. So what I thought was, get out of this conventional drug discovery process, which is go behind a known biomarker. So how about go to the cellular level? Because my technology can compare two cell surfaces in a very high accuracy, very high sensitivity. So what we did was, we separate cancer stem cells from same patient, same tumor, and then we stain these cancer stem cells in red. The remaining cancer cells from the same tumor in green, mixed 1-to-1 and exposed to the library. And if we see only red cell bound bead, like on the right bottom middle area, what does that mean? That means the compound on that bead binds to something on cancer stem cells, which is not found in the remaining cancer cells. And that something can be, the cool thing is that something can be a protein, lipid, carbohydrate, or anything. So the conventional drug discovery is kind of reversed here. We go back and then we can pull down and identify that. So that's the idea. So we had a very good cell pair from the UT Southeastern Medical Center, and after developing this technology, actually I got open to the second largest cancer cell collection in US. So we use this, the lung cancer model. And again, to cut a long story short, I will go through this data very rapidly because I just want to show that. So we found one compound, and then the idea is to, actually we showed that it targets only the cancer stem cells, it doesn't affect the normal stem cells, which is very, very important for us. And then we showed that these pull down cells has stemness properties. And then, according to the way we did this screen, we don't know what is the target, right? We only know it targets cancer stem cells. The way we identify those targets is we let the compound to bind to the cells and then chemically trigger cross-linking with the target and then pull it out and identify what is it. So that's what we did. So the other cool thing with my technology is we find the target and a compound to target that at the same time. So and it can be a new protein. And in this case, we found actually a new biomarker for cancer stem cells. The protein is plectin, which is known. What happened with this plectin is it's a structural protein found inside of the cell, and it actually formed the structure. So these type of biomarkers are not targeted by the conventional drug discovery because it's found everywhere. But the cool thing is it comes to the cell surface during the cancer spread, cancer metastasis. So that's what we found. So after that, we actually showed a lot of things. I'll go rapidly with this data. We showed it actually very important for stem cell survival and stem cell migration, because that's what the metastasis does. And this is real patient data. If this biomarker is high, the patient survival is very low. So this has a very direct correlation with the patient survival. And then actually we showed that our compound can very specifically kill these cancer stem cells, and it doesn't affect the remaining cancer cells. So this is very, very specific for cancer stem cells. And here actually I'm showing how this colony formation is being destroyed. If you look at the second panel, with the increasing concentration of the compound, you can see the stem cell colony formation is being destroyed. And here actually I'm showing our compound can actually block these cells migration. Now that's the first step of the cancer spread, the metastasis. So it actually blocks that step as well. And most importantly, we did the preclinical animal studies and showed that our compound actually blocks the tumor growth in the mice. So this is the summary of that project. We did the complete unbiased selection and found a new biomarker for cancer stem cells. Actually, we published this in Nature Scientific Reports, and it became top 100 downloaded papers in 2019. And we have shown that it actually is now working on the preclinical level. Okay, so let me go through two more very rapidly on two other projects using this technology. And this project, we did the same approach just to target cancer cells compared to the normal cells from the same patient. So we use 2 cell lines from the same lung of the same patient. Again, we did the red and green screen. We found a compound. This actually about 400,000 compounds screened on this project. The previous one also kind of similar. And then we showed our compound binds only to the stem cells. The cancer cells, not to the normal cells. And then we try to do the same thing like we did in the previous study, which is to let it to bind to the cells and try to pull down the target. We couldn't identify any target. That is good and bad. The bad is it looks like we don't have it looks like an unknown target. But the good side is that way we only find protein targets. The proteins are the most common targets that is used in the drug discovery, right? Targeting hormones, enzymes, signaling molecules. But I told you, cancer is very complex. We need to go beyond that. And I'm very glad to say that our compound, when we did this complete unbiased selection, was targeting a lipid. And it's a very unique lipid. In the cell membrane, there are 4 lipid types. One of them is phosphatidylserine, PS, which is found in the inner layer of the normal cells. So it's not exposed. But in cancerous situation, this lipid comes to the cell surface. And it is actually a signal to natural killer cells to say, don't kill me. That's a signal that uses to evade the immune system. So what happened was, when we did this complete unbiased comparison, we found this compound binds to this lipid. And then you can see it's very specific because it only found in the cancer cells, not in the normal cell surface. And then actually it has been reported that this lipid is found almost every cancer. So that's another very huge thing, because protein biomarkers are different from cancer to cancer to even person to person. So if we develop these compounds into the drug, actual drugs, it can be used as a common treatment. Anyway, that's a long way to go, but we showed the activities in various levels, in animal level, and here actually I'm showing the activity, the tumor burden in mice, preclinical level. So again, the summary is, we found with a complete unbiased selection, a compound that binds to this lipid very uniquely transferred from normal inner layer of the normal cell to the outside. So let me talk about the very last project. This is another interesting project that I did for targeting, for the diagnostic purposes. So this is the common cancer diagnosis curve, and you can see the number of cells and the time is plotted, so how the cancer grows, and there's a very sharp growth with this angiogenic switch. The VEGF receptor that I mentioned earlier, it actually supports the new blood vessel formation towards the tumor, and that really increased the tumor growth. And then you see the death of the patient. And now you can see the current detection level, which is after the angiogenic switch, which means we are very close to the death of the patient. So how we can bring this bar down? So not only me, there are a lot of researchers trying to do this. So the common typical way of doing this is, again, you want to target the biomarkers, right? So how do we find these early biomarkers? So the conventional way is, again, if you have a list of cancer biomarkers, let's say 100 or 1000, what scientists do is see how many of them show up in the early tumors. That's the conventional way. And are we sure we know every biomarker? That is the question I have. And also this is again a biased approach. So what I thought was, so this is the tumor growth process starting from a very normal cell and goes through these pre-neoplastic cells that are acquiring various mutations, and then after some time, after that right two areas, after that angiogenic switch, it becomes a very active tumor and it grows rapidly. But if we want to identify very earliest biomarkers, we want to target these very early level cells. We need to study them. Actually, there are so many people trying to study them. So my approach was to do this in a very interesting way. So what we did was, with the help from a collaborator, we developed these cell lines. So we start from this normal lung cell, primary cell from a patient, not a patient, the normal cell, and then we gave 3 key mutations that drive the tumorigenicity, one at a time. So we gave the first P53 and developed a cell line. KRAS, CME, those are the 3 major mutations happen in most of the cancers. So by this way, if you go from top to the bottom, we stepwise transform a normal cell, fully normal cell, into the cancerous situation. Now my hypothesis was, these tumor mutations happen inside the cell, and when this happens, the cell start becoming a cancer and it start initiating new signaling pathways, all these things needed for tumor growth, and that changes the cell surface. So that comes back to my technology, because if I compare that normal cell with any of these cell lines, it's starting now start changing the surface, and that change is due to cancerous situation. And that those are the very earliest biomarkers. That's my hypothesis, and can we pick them? And if we pick them, it's a real-time earliest biomarkers. So it's like we kind of poke a person and make him angry and say, oh, he's angry. It's like that. So that's how we try to pick it in a very normal, the natural situation. So with that, with my technology, I can compare normal cell to the next cell, and then normal cell to the next level, and come normal cell to the next level. So by doing that, we can pick real-time new biomarkers are appearing, and they are the earliest biomarkers for cancer. So that's the idea. In the first project, we actually compared the fully normal cell to the fully cancer transformed cells. And again, red and green screen. Red is the cancer cells, fully transformed cancer cells. Green is the normal cell. We compared it, and again, to cut a long story short, we found several compounds, and one of them actually, again, we don't know the target, right? We don't know that. And then we did the same pull down and found this protein, which is vimentin. Now, this vimentin also a non-biomarker for later stage of the cancer. In the metastasis, this is a very, very important protein in the EMT process. But we found this is this is expressed in the very, very early cells also. So, and also in the cell surface. And then after that, actually, it's the application of various diagnostic and therapeutic. So, we did the diagnostic application, and this is actually the normal IHC histopathology application. So the bottom panel is the use of the conventional antibodies for the histopathological the identification, tumor identification. The top panel is our use of our compound. It is very similar. First four are the cancer lines. The rightmost one is the normal cell, so it doesn't stain normal cells, but it stains all the cancer cells, comparable to the conventional histopathological antibodies. So we can replace those very expensive antibodies with our compound. And this is actually very early stage. I'm trying to develop a simple blood test type diagnostic test that we can use to identify the cancer. That is far, far away, although it's very enthusiastic that there's no such a simple drug is available. This testing method is available. So these are very early data. And then we showed that this compound, again with some chemical modifications, kills cancer cells as well. Not only the diagnosis, but in the therapeutic side as well. And here also I'm showing that the same colony formation is being destroyed with the increasing concentration, and then it actually blocks the cell migration. And we think this is also has an effect on the cancer stem cells too. So as a summary, so we actually compared the fully normal cell to the tumor transformed cells and identified a new biomarker for early cancer detection. So if I summarize these technology applications, so these so far I have 8 patented compounds, and these are 7 of them I'm showing targeting protein biomarkers on cell surfaces, mainly in cancer, and also in some of them are applicable in COVID-19 as I mentioned, and also some in the Alzheimer's and also even sepsis. We have some very interesting data recently. And then we targeted the lipid also on the cell surface, very unique lipid. And we do a lot of diagnostic side as well. I didn't have time to talk about all those projects. So this is kind of a summary of the outcome of this technology, which is now used in US and worldwide as a technology that we can try to identify drug leads that has least off-target effects at the very first day of the screening. So as I mentioned, in my lab we do 100,000 compounds per day, and we are trying to automate the system to increase the outcome further. So these are the levels of those current projects, showing from initial discovery to the clinical level. All these patented compounds are now in the preclinical level. Some discussions going on getting into the clinical level. So I have shown only 4 projects, and there are all the other projects are there. And I want to finally thank all the people who has done this work. I'm just sitting in the office and plan all those. So these people who are working in my lab, the postdoctoral fellows, the PhD students, the technicians, and there are a lot of people who has really worked hard in the lab to all this, and I really want to acknowledge them. And also I want to thank all my collaborators. So no individual can do things alone. So the success in US is that we always collaborate, and there are a lot of groups working together. So, and I want to thank all my collaborators throughout US and the other countries, and then actually the most importantly the funding. So this mainly from NIH and also the CPRIT. I want to just mention that the CPRIT means Cancer Prevention and Research Institute of Texas. So it was built by the people in Texas. Vote, actually they vote and tell the government to spend $3 billion in cancer research, and then they create this Cancer Prevention and Research Institute. And I want to mention, it was not named as Cancer Research and Prevention. They used the prevention word first, and there's a message. So we really need to think about prevention, because it's a very complex situation. So there are a lot of steps being taken in US for this cancer prevention. So I just want to mention, and there are many other funding sources. I want to acknowledge that, and I think that's all I want to tell. And I really again want to thank for your patience, and also for the organizing committee for inviting me to deliver this talk. And it's very glad to be here, and I always like to come to Sri Lanka and do this, and it's so I have to leave within a day. It was initially I was supposed to go right back to the airport, but I'm leaving tomorrow. So I want to wish good luck for everyone, and if there are any questions I can answer. Otherwise I can stop here. Any questions? Okay. Thank you so much, and good luck.
That was Professor Gomika Udugamsurya, and he was talking about the wisdom beyond chemistry, novel technologies to expedite the modern drug lead discovery process. Thank you very much, sir. On that note, ladies and gentlemen, let's now appreciate our keynote speaker, Professor Gomika Udugamsurya, and to do so, I cordially invite Senior Professor Sujeeva Amarasena to symbolically give away the token of appreciation to Professor Gomika Udugamsurya, Associate Professor, University of Houston, USA. Thank you, everyone. Next, the highlight of today's proceeding is the address by the chief guest. For that, I respectfully invite our chief guest, Senior Professor Sujeeva Amarasena, the Vice Chancellor of University of Ruhuna, to address the gathering. Over to you, sir.
morning to all of you. Professor Ruhuna Surya, our keynote speaker today. Professor Himali Munasinghe, Dean Faculty of Science. Chairman of the Organizing Committee, Nayanda. Senior professors, academic staff members, and members of our executive staff, students, ladies and gentlemen. Let me thank the organizing committee in the first place for inviting me to be the chief guest today at this 10th International Conference, Science and Technology Conference in the Faculty of Science, University of Ruhuna. I think that it has been a privilege to watch and participate in meetings, conferences organized by the Faculty of Science over the last so many years as a Vice Chancellor and participating in each event. And in every event had been very well organized and well conducted with lots of attraction, I must say, that receiving 170 abstracts and having to vet almost 1/3 of those abstracts is a tough job, but a good job at hand, although it's a headache. It's a good headache to have because I think many conferences do not attract that much scientific abstracts and work. So, many congratulations to Faculty of Science and the organizing committee. With that, let me move on to your own theme, advances in scientific research for sustainable environment. Now, all of us are concerned about this. We are concerned about our environment. We want to protect the oxygen we breathe, which we get free of charge. Without environmental challenges that we have encountered by perhaps our own actions, preventing us breathing that free oxygen. It has come to that level today. So, all of us as individuals, whether we are scientists, whether we are administrators, whether we are ordinary people, must be concerned about sustainable environment and we need to get educated about it. Of course, I think many people have realized that sustainable development and sustainable environment is not possible without all of us getting together from multiple disciplines, multiple partners, and everybody at every level, from politicians to ordinary people. So we need to get together to work towards protecting and making our environment sustainable for future generations. To me, sustainable environment is basically utilizing resources of the environment for our survival without compromising the future generations in their survival. But they will need same resources to survive, and if we utilize everything, the future will be bleak. Now, therefore, we need to ensure that food supply is secured for future generations and we will not destroy it, and so are other things. How do we do this? All of us probably know with a lot of research on how to do a lot of things to sustain the environment. However, we have a serious attitudinal barrier in our country, not only in our country, everywhere in this world, where people don't come together to work together for a common goal. And I think we see that more in Sri Lanka, perhaps, than in many other countries, maybe with our experience. Maybe we are wrong, maybe some other countries have worse problems than us. But I think we as an educated society should be able to understand that we need to come together and work together from various disciplines, from engineering to science to agriculture to medicine and humanities, management, get together and work towards this particular goal. And I think that is the biggest challenge all of us face today. It's not research that we face. I think research can follow it. If you can resolve that particular issue, today the research and advancement of research and getting together to do research for needs and applied and application will automatically follow that path. So may I request that all of you who have gathered today here physically in this meeting and all of our other members scientific committee, all the other members in the scientific committee have joined us online, join hands together to change this world, transform this community, to partner and collaborate with each other and support each other in promoting a sustainable environment. Be it climate change, be it weather issues, whether it be disasters, be it many things. I think that's the first thing to start. From there, I would like to say that we probably have the answer for the sustainable environment. Only issue is we do not know how to manage it for our developmental needs. So I think the answer is nature. Nature, I think, is the best engineer in the world. Nature, I think, is the best scientist in the world. Nature, I think, is the best doctor in the world and the best manager in the world. If we can mimic nature in every developmental activity, or try and mimic the nature or natural processes all the time in our developmental activities, then I think we will be able to sustain our environment without compromising the needs of the future generations. And I think that concept is called biomimicry. That concept is called in design science biomimicry. You mimic the nature in every design, every activity. And we can do that. And we can do that. For example, I think you go to Sigiriya, you find a faculty of engineering there. You go to many such natural creations, environments, you find the best botanist or the scientist or zoologist there. This morning we were talking about our own crocodiles in River Nilwala River and also Pohapur, and how crocodiles lay eggs and how many legs they lay and the number of offsprings coming out of those eggs. So I've been told that only a very small number of eggs ultimately hatch, and these eggs are hidden, and so that no other animal can come and eat or what. And then same crocodiles eat their offspring, so they control their own populations. We have to discover artificial methods of controlling our own population growth. They do it themselves, maybe they are doing it to prevent food shortage with long survivals. So that's nature. So it has created its own way of managing their own environment. I think we need to think in the same way for sustainable environment. So we do have a lot of disasters on our way. We've been ranked number 2 for disasters due to climate change in the world by some organizations. So we have to expect a lot of problems, be it climate change, be it weather, be it disaster. We as an educated community need to get prepared in advance, ensure that data and information and signals are taken seriously and acted upon immediately without being negligent of our own duties as scientists. And I think if you can take a lesson from Easter Sunday attacks, and that's what Supreme Court has very clearly stated in their judgment. You got to do a job, and if you don't do that job, and if there is a negligence, then you got to pay. And I think if you look at lots of things that happen in this country, not just politicians, our own government service, universities are failing in our own duties with regard to the signals that we receive and ignoring those signals, allowing disasters to happen. So that's where we need to become a little more responsible, or lot more responsible as scientists and academics in our community. Right. The last point I want to make or stress upon you is about ideas and feasibility. I'm sure you all listened to the speech of Professor Komika Surya at the beginning. Said, I put down 50,000 ingredients and get one drug, or 10,000 ingredients and one drug at the end of the day. So that's wastage, money, and everything else. I can give us examples and that for you to consume. But as a country, I want you to understand this particular concept. As a country, we do promote ideas. We have lots of ideas how to do things, how to change things, how to make things happen. Of course, we have two kinds of situations. One is a situation where there is lots of scientific research evidence available, and still we are not promoting ideas based on evidence created by scientific research, and just promoting ideas. Other side is ideas when there are no research, or no research has been conducted and no research evidence is there, and you still have to change something, and then you try your own ideas to change things. So in the second situation, feasibility studies need to be carried out. In the first situation, if you have scientific evidence, you need to get that scientific evidence and implement it. Because scientific evidence is there. Now, next question is feasibility. Can it be done? You try and do that and implement it. It should change things. If not, scientific evidence has failed. And then you need to find out why it failed. Other side is without doing any kind of feasibility, promoting ideas to change something, and that idea doesn't work, and we waste a lot of money on that. And we waste a lot of money, and ultimately it ends up in disasters. So in Sri Lanka, we do encounter and experience that concept being implemented at every level, government level, university level, and many other levels in the country. As a country, we need to rethink about these things, and these things do happen everywhere, and that includes projects that ultimately have an impact or are aimed at protecting environment or have an impact on sustainable environment. I think that is something that all of you need to rethink when you get involved in something, as scientist and something that I should be thinking about when I get involved in something. For example, I can think of taking all 12,000 students of University of Ruhuna and going and cleaning up Ruhuna from all plastic and other rubbish that is there, because I think that's a place that attracts tourists and also is a very important place for our country, and we really need to protect that area. But how costly it is. Will that have a big impact? If I say put it on newspapers, 12,000 university students are going to clean up Ruhuna all at once, on a given day. I'm sure we can definitely clean up entire Ruhuna with that crowd. Will it be sustainable? Will it work? How much money will we spend on that? And will others learn that lesson? Will the communities take over from there to maintain that cleanliness? Now, those are the kind of things that I think we should be thinking of before implementing any project. Although a project like, say, taking 12,000 students from Ruhuna and cleaning it up, and looks very attractive, very beautiful, very politically, can be sold very quickly. But it does have its own disadvantages. So that's basically what I want to say about ideas and feasibility, implementation, research, science, and sustainable environment. We need to get together, sit down, work, and see what could be done to protect, and start it from our own garden. Don't go anywhere. Start it from our own land. University of Ruhuna, I am very worried about our own environment. Cleaning it up, ensuring that we are plastic free, we are collecting garbage properly and disposing waste and managing waste very well. Let's start from here and then take it outside into our perimeters, inch by inch, into the community and everywhere else. If you do that, using our own scientific evidence, using our own human resources, using our own, or maybe some generated funds from everywhere, we will be able to do this. So I think with that little note, I will conclude my speech. I wish to congratulate the organizing committee for organizing this event, and I wish you all the best. Thank you.
Thank you very much, sir, and we highly appreciate your presence here today. We have come to the end of today's inauguration session. The Ristcon 2023 is a result of a number of individuals joining hands together with us. So it's time to appreciate the advisory and the editorial board and all our sponsoring partners. For that, I cordially invite Dr. N.T. Vikramasuriya, Joint Secretary of the Ristcon 2023, to deliver the vote of thanks on behalf of the organizing committee.
Good morning, everyone. Our chief guest, Senior Professor Sujiva Amrasena, Vice Chancellor of the University of Ruhuna, Professor D.H.A. Munasinghe, Dean, Faculty of Science, University of Ruhuna. Our keynote speaker, Professor Ruhuna, Associate Professor, University of Houston, USA, and all the distinguished invitees of Ristcon 2023. It is such an honor for me to get this opportunity to thank you all dignitaries on behalf of the organizing committee Ristcon 2023. I extend a warm welcome to the people in the gallery. I would like to express my gratitude to all esteemed delegates of the conference for their presence and contribution to make this conference a great success. This is a challenging time for all of us due to the economic crisis and pandemic. Therefore, Ristcon 2023 had been organized as a hybrid conference for the third time. We have organized this inauguration ceremony physically with limited number of invitees, while the technical sessions will be held online. As the Joint Secretary, Ristcon 2023, I would like to take this opportunity to extend my heartiest gratitude to all who have supported to make this event a success. I extend my gratitude to our chief guest, Senior Professor Sujiva Amarasena, Vice Chancellor of the University of Ruhuna, to take out time his busy schedule to grace the event. We highly appreciate your leadership, encouragement, and extensive support to make this event a success. Next, I immediately thankful to Professor E.P.S. Chandana, Deputy Vice Chancellor of the University of Ruhuna, for providing his immense support to make this a successful event. Furthermore, I would like to express our profound gratitude to Professor D.H. Narasimha for her leading supervision and inspiration at every point of the event. With a deep sense of appreciation, I am so thankful to our keynote speaker, Professor Gomika Surya, Senior Professor, University of Houston, USA, for accepting our invitation despite your busy schedule and sharing your valuable thoughts with us on the topic of the wisdom beyond chemistry, novel technologies to expedite the modern drug-free discovery process. Further, my sincere thanks goes to plenary speakers, Professor Buddhi Marade and Professor Chandima Gomez, who will be sharing their work and opinion at the conference dedication in the sessions. It is a great pleasure to say thank you to all members of Advisory Board and the Editorial Board for their enormous support and guidance to our conference. Furthermore, I would like to extend my acknowledgements to all the external and internal reviewers for rendering their valuable comments in time and help to improve the quality of papers present in Ristcon 2023. I will be failed in my duty if I do not underline a very important role played by all authors and participants from various backgrounds. Without you, the conference would not have been a reality. Further, I sincerely recognize the constant support given by all the internal and external professors, academic staff, and academic supportive staff who accept our invitation to participate in Ristcon 2023 technical sessions as panel members. Thank you very much. All this would have been impossible without the financial support given by our sponsors. We recognize Bank of Ceylon, Nippon Brain Fiber Limited, Foundation Trust Sussex, UK, People's Bank, Harishchandra Mills PLC, Sri Lanka Insurance Corporation, Sri Lanka Telecom, and Hemsons International Private Limited. With gratitude, their significant contribution. Next, I am extending my deepest thanks to Acting Registrar, Librarian, Deputy Registrar Legal, Acting Assistant Registrar of the Faculty of Science, Deans of Faculties, Directors of Quality Assurance Cell and CETA, and Heads of the Department of University of Ruhuna for kindly grace this event with your presence. I also extend my thanks to all academic staff, academic supportive staff, demonstrators, non-academic staff, and students of the Faculty of University of Ruhuna for their tremendous dedication throughout this event. In addition, I must be thankful to Photographic Society, Faculty of Science, Media Team, the Cultural Center of the University of Ruhuna, Maintenance Unit, Suppliers and Finance Branch for their support to make this as another important successful event of the University of Ruhuna. I'm also thankful for the administration in general for rendering us all possible logistic support towards organizing this event. Well, an event of this much dimension cannot happen overnight and needs meticulous planning and execution. The wheel starts rolling months ago. We have been fortunate enough to the back of the team of very important and motivated colleagues. I cannot thank each one enough for their involvements. They have shown us and the willingness they have expressed to make on the completion of this work beyond their comfort zone. So I mention my deepest sense of appreciation and would place on my record hearty thanks to all the members of the organizing committee Ristcon 2023. I once again want to state that we are grateful to all of the distinguished guests present here by accepting our invitation. Finally, I believe Ristcon 2023 will become a great platform for all the young scientists who have joined us to share and exchange their knowledge and innovations. Once again, I thank all of you for your cordial cooperation and have a nice day. Thank you.
Thank you very much, Madam. Here's a kind reminder to everyone. Please also be noted that the first half of the technical sessions will be starting at 11 a.m. and the second half will be starting at 2 p.m. You can join all the sessions virtually, and there are two plenary sessions. The first one, starting at 11 a.m., will be strengthening the food system in Sri Lanka to overcome the food crisis by Senior Professor Butti Marambe, Department of Crop Science, Faculty of Agriculture, University of Peradeniya. The second session, starting from 2 p.m., will be seeking the contribution of cross-disciplinary researchers to address the energy crisis by Professor Chandima Gomez, Distinguished Professor, University of Witwatersrand, South Africa. Ladies and gentlemen, all good things must come to an end. That's a well-known proverb. And on that remark, to end up the inauguration ceremony of the 10th Ruhuna International Science and Technology Conference 2023, please rise from your seats for the national anthem of Democratic Socialist Republic of Sri Lanka. Thank you and have a nice day, everyone.